Hello.
Hi.
How are
Hello
you?
there.
Hello. How are you guys?
I'm doing alright. How
Good.
about you?
Doing well, doing well. Let's
Nice.
see. Yeah. Um.
I'm eating
So,
right now, so sorry if you hear it sounds from my mic, alright?
oh, it's
I'm
okay.
eating right now.
Are you eating?
Yeah, I'm
Okay.
eating right
Yeah,
now.
that's okay. That's okay. Yeah. So, like, I think you wanted to go over the homo-lumo theory of the electrocyclic reactions.
Yes, please.
And deals.
Actually, just whatever we needed to know about it. Like, if you just want to explain it like vocab style, that's also okay.
Yeah. It's gonna be more conceptual stuff because like you don't need to use this homo-lumo stuff for predicted product. For predicted product, you could use the tables that we used before for the ring closing, ring opening, and for deals order, it's like you don't have to use the homo-lumo stuff. So it's more
Got it.
conceptual vocab style, right?
Okay.
So uh, let's explain it in terms of deals order because that's gonna be easier to explain.
Thank you.
Yeah, no problem. Right. So deals order, we said that it's going to react with a diene and a dienophile. And if we put heat through that, then we're going to get some kind of cyclohexene, right? But the diene right here, we could have something called the S-trans configuration, or we could have something called the S-cis configuration, right? And what that means is that our line of reference is going to be down the sigma bond between the conjugated diene between the two alkenes, right? So these lines here that I'm drawing are the lines of references, where we see that this is S trans on the left side because the two double bonds are on opposite sides of each other. They're trans to each other. Whereas the two double bonds here are on the same side of the line to each other, making them S cis to each other, right? S, you could think of it as like sigma bond. The sigma bond right there is in reference to that sigma bond, right? So in Diels order reactions, the S cis diene will react, right? If you have an S trans diene, that S trans diene will not react, right? So if you see an S trans diene like that, that would not react with a dienophile unless you put enough heat for it to rotate that S trans diene into the S cis diene, right? You could rotate that sigma bond into this S cis diene, but it's going to require a lot of heat, right? To rotate this S trans diene into the S cis diene, you need high heat to add enough energy to rotate that, right? But if you have a locked S trans system, oh yeah, the website reacts these to see the different chemical structures and formulas and the properties of them. Yeah, that's a good website. Yeah, that's good. That's good. Yeah. Does your dad work at an institution like a university or something? Yeah. So let's say we have this S trans diene system right there. This is locked. We cannot rotate this sigma bond because it's in a ring. Cannot rotate. So this S trans diene will not do a Diels order reaction. Okay. And let's just put a dienophile like that. So conceptually, the HOMO of the diene will react with the LUMO of the dienophile, right? Let's make that clear. HOMO of diene reacts with LUMO of dienophile. So let's see what that means. Right. Oh yeah, that's good. Yeah, right. Because when you have like an email where like on college, then you can use like the free the resources for free, right? So HOMO is gonna be highest occupied molecular orbital. Yeah, molecular orbital. LUMO is going to be the lowest unoccupied, because of the U, unoccupied molecular orbital. Okay, so let's look at the diene system. This diene system here has 4 electrons that are conjugated to each other. 2 from this double bond, 2 from that double bond. So if there's 4 electrons in the resonance structures, right, there's going to be 4 atomic orbitals, which is equal to the number of molecular orbitals. So we have 4 molecular orbitals. Right, so let's draw in those 4 molecular orbitals in like this. One, two, three, 4. And then let's draw out 4 orbitals here. Right, and then energy is going to go increase from down to up. So this is representing energy, this arrow. Right, where this bottom molecular orbital here will have the lowest energy, and this highest molecular orbital here will have the highest energy, right? So the lowest energy will have no nodes, and as we increase the level of the molecular orbital energy, we're going to increase the number of nodes. So we're going to go from 0 nodes to 1 node, right? And then if we go one more time, 1 node to 2 nodes, and then 2 nodes to 3 nodes, separating all of these orbitals here. So the bottom lobe, since there's no nodes, all of the p orbitals are going to be adjacent to each other, right? They're going to be in conjugation with each other, flowing throughout the whole system, right? Now, when you introduce a node, that's going to separate the flow, right? So since there's a node there, the electrons are now going to go up right here, right? But there's no node between the rightmost two, so these two are going to flow with each other, right? So let's say this is down, this is going to go up, the next one stays up because there's no node between them. Right? And these shaded regions here are representing the electrons, where the electrons are going to be at, right? Since there's a node there, the electrons are going to be separated from each like orbital, right? And the highest molecular orbital, like highest energy molecular orbital, all of the p orbitals are separated by nodes, right? So this is the least stable because it has the least amount of conjugation resonance. They're all separated like that, right? So a way to think about this is that the lowest energy, we see that everything is flowing within each other. So if we draw in our diene like this, the electrons here are flowing all throughout the system, right? So this is also known as the resonance hybrid, of the diene. But if we increase the node right here, now we see separation between the two atoms, right? Which that's going to represent this right here, because we see these two p orbitals here overlap with each other, which is this two p orbitals overlapping with each other there, right? And then these two p orbitals here that are overlapping with each other are these two p orbitals here that are overlapping with each other, right? There's a node in between those two sets of orbitals, and that node is represented by this sigma bond right here, right? There's no electrons flowing through there as it's drawn right there, right? Whereas every single p orbital on the lowest energy molecular orbital is flowing to each other. So the electrons here are represented as flowing all throughout the structure, or the resonance hybrid. Right? That's why double bonds are more reactive than single bonds. Yeah, double bonds are more reactive than single bonds because they have more electrons here, and these electrons here can be nucleophilic, which can act as electrophiles, which can attack electrophiles. Single bonds, there's like nothing going on in single bonds. The only reactions you can do with single bonds are free radical halogenation with X2 and light, or if you have an unstable cyclopropane or cyclobutane, you could break it open with H2 PDC. Right? So not a lot of reactions with single bond alkenes. Once we move on to the higher energy level molecular orbital, we're going to let's say draw this resonance structure here, right? Pop that double bond over there. This double bond will pop onto that carbon to get this molecular orbital here, right? Where now we see that these two p orbitals in the middle that are overlapping with each other are those two p orbitals here overlapping with each other, making that double bond, right? The separation of charges are at the ends, right? These end p orbitals here are separated from each other. Now, the highest energy molecular orbital is when every single charge is separated, right? And we learned in 118A that the least stable resonance structure is the one that has the most amount of charges, right? This is the least stable resonance structure. This is the most stable resonance structure at the bottom because every single thing is flowing, right? Okay, so that's how we could think about it in terms of energy. As you increase the number of nodes, the separation increases, which increases the energy or decreases the stability, right? And since this diene has 4 electrons in the conjugated system, we fill in each of these orbitals 2 at a time. So that's 2, and that's 4 to represent the 4 total electrons in this conjugated system that are moving around in the system, right? So now notice how we have occupied region, right? Occupied, which means that these orbitals here are occupied with electrons, and an unoccupied region, right? These orbitals here are unoccupied with electrons. There's no electrons there, right? So this orbital specifically is going to be your HOMO, right? Or the highest occupied molecular orbital, right? Comparing these two molecular orbitals here that are occupied, the one on the top is the highest one in the energy scale. So that's the highest occupied molecular orbital, the HOMO. Okay. This one right here specifically is the LUMO, the lowest unoccupied molecular orbital. So the confusing thing here is that when people see like the words highest and lowest, some people might think that the highest occupied molecular orbital is higher in terms of energy, right? But that's not true. the lowest unoccupied molecular orbital is higher in energy. We see that this LUMO here is higher in the energy scale than the HOMO, right? So let's say the LUMO energy is higher than the HOMO energy. Okay. So that is the molecular orbital of the diene. Let's look at the dienophile, which is going to be more simple because there's only going to be 2 electrons in the conjugated system. Well, not conjugated system, but two electrons that could do resonance. Right. So let's say we have a simple diene like that. We only see 2 electrons here that can do resonance like that. Right. So if there's 2 electrons, there's 2 atomic orbitals, and that's 2 molecular orbitals as well. So 1 molecular orbital is there, the other molecular orbital is here, 1, 2, right? Energy scale. And the lowest molecular orbital has no nodes. We increase the molecular orbital, we introduce 1 node right there, right? And then that 1 node separates the charges. So let's say if that was going down, the other one is going to go up. Every single thing is separated, right? Whereas the bottom molecular orbital, there's no nodes, no separation of charges. These 2 p orbitals here are going to be flowing with each other, adjacent to each other, conjugated with each other, right? So to represent that, we could say that that is like basically this. And then when we do resonance like that, the charges are now going to be separated, right? We see that this resonance structure here is less stable than this resonance structure here. And because this is less stable, it has higher energy. It's higher up in the energy scale, right? Because energy and stability are inversely related. And we said that there's 2 electrons in the system. So let's fill in those 2 electrons in the molecular orbital, right? 2, and we're done there. Now, this is the occupied region, and this is the unoccupied region. So that makes this the HOMO and this the LUMO, right? So we saw that the dienophile is much more simple than the diene because there's less electrons to deal with, right? Less molecular orbitals to deal with, right? Okay, so now let's explain why the S-cis diene is required for Diels-Alder reaction. Right, so if I draw in an S-cis diene like this and draw out its p orbitals, let's say let's draw out in blue, right, and then draw in the dienophile in this projection, right? So imagine that this diene right here is hovering over the dienophile, right? It's going above the dienophile. And let's draw the dienophile's p orbitals like this, right? And we said that in the Diels-Alder reaction, the HOMO of the diene reacts with the LUMO of the dienophile, right? So let's draw in the HOMO of the diene, right? So the HOMO of the diene, we saw that it had 1 node in the middle right there, right? So when I draw in the shaded electrons, let's say that these 2 here are going down. That makes the other 2 go up because of the node right there that's separating them, that's separating those 2 sets. Right, so that's the HOMO of the diene. This is the HOMO of the diene. Let's draw in the LUMO of the dienophile now, right? Which is like this. The LUMO of the dienophile is also separated by 1 node in the middle, right? And this one right here, we have to make the bottom lobe overlap with the top lobe, right? The bottom lobe of the diene has to overlap with the top lobe of the dienophile, right? So these has to overlap. So to make them overlap, this one here has to go up, the electrons has to go up, and then since there's a node right there, the electrons on the bottom has to go down, right? Now we see that these two lobes here are overlapping with each other, right? They have the same configuration. There's electrons here, there's no electrons here. That's the direct overlap that they need in order to do an electrocyclic reaction or pericyclic reaction, right? Electrocyclic is like the ring opening, ring closing. I think Diels order is like some pericyclic reaction. Let's see, Diels order. Reaction. Let's see what it specifically is. I think it's like from 6 numbered rings. Four types of pericyclic reactions. Electrocyclic, which is the ring opening, ring closing. The other three are cycloaddition, sigmatropic, Ene reactions. I don't think you guys need to worry about that. Just worry about the electrocyclic, ring opening, ring closing. But I'm trying to figure out what specific type of pericyclic reaction is a Diels order reaction. What specific pericyclic reaction is Diels order? Okay, so Diels order is going to be considered four plus two cycloadditions, or specifically, more generally, cycloaddition. Cycloaddition. Four coming from the diene, 4 electrons. Two coming from the dienophile, 2 electrons. More generally, cycloaddition, right? The electrocyclic reactions are a type of pericyclic reactions, and cycloaddition is also a type of pericyclic reactions. Right. So what I mean by that is pericyclic reactions. There's 4 types. There's electrocyclic, there's cycloaddition, there's sigmatropic, and there's Ene, right? Don't worry about sigmatropic or Ene. But you guys did learn about cycloaddition or electrocyclic, and more specifically for electrocyclic, you guys learned about ring opening and ring closing in heat or light giving counteratory or distillatory configuration. Cycloaddition, that you guys learned specifically 4 plus 2, or aka Diels order. Right. Okay. Yeah, so that's why this S-cis configuration on the diene is required, because let's say that we drew the diene in the S-trans configuration, right? And then we draw in still the homo of the diene and the LUMO of the dienophile, like this. Right? We see that these two lobes here do overlap, have a direct overlap, but this right here is too far away for the homo-lumo interaction. Right, so no reaction. Right. That's why for Diels order, we need the S-cis diene in order for the homo-lumo to overlap and interact with each other. Okay, yeah, so that's the concept of the homo-lumo theory. This would also apply to electrocyclic reactions as well. You could just think about this homo-lumo interaction right here, the direct overlap between the lower lobe of the homo and the higher lobe of the lumo has to interact with each other, right? Because this is the homo right here. This is the lumo right here. They overlap with each other like that. Yeah, so this is more conceptual vocab. I don't know how Leavens asks for it yet because I haven't checked the practice exam, but we'll see what she wants with this concept. Yeah. Okay. Any questions on this? Uh-huh. Yeah, no problem. What other? I'll be right back. I'm gonna get water really quick. Ooh, aromaticity and electrophilic aromatic substitution. Yeah, let's do that. Chapter 15. Okay, okay. Did you guys finish chapter 14 material in lecture yet? Okay, that's good. That's good. So there is another chart to determine whether a molecule is aromatic, non-aromatic, or anti-aromatic. Right, those three things. So aromatic, uh, anti-aromatic, or non-aromatic. Okay. right? So here's the table here. Anti-aromatic and non-aromatic. Okay. You could think of the number of electrons as 4n plus 2 or 4n, right? But the way that I like to think about this is that for the 4n plus 2, it's going to be the odd pair of electrons. Wait, not individual electrons, but a pair of electrons. Odd pair of electrons. So this is like the table that I gave you guys last night for the electrocyclic ring opening, ring closing reactions. It's going to be the same, similar concept, right? And if you see 4n, that's going to be an even pair of electrons. Non-aromatic is going to be either or. It could be 4n plus 2 or 4n. Doesn't matter. Right, so any kind of electrons. Right. So to be considered, let's say, aromatic or non-aromatic, you have to fulfill these three conditions here. The molecule has to be cyclic in a ring. It has to be planar. Everything's flat and planar. And it has to be fully conjugated. Right? No sp3 roadblock in this ring, in this cycle. Fully conjugated. If the molecule is missing at least one of these, right? Like let's say it's cyclic and planar, but it's not fully conjugated, then it's automatically non-aromatic. Or if it's fully conjugated and cyclic, but it's not planar, then it's non-aromatic, right? So you need to fulfill all of these three conditions in order to be considered either aromatic or anti-aromatic. And to differentiate between aromatic and anti-aromatic, you look at the pairs of electrons in the resonance or in the conjugated system, right? Odd pair of electrons, aromatic. Even pair of electrons, anti-aromatic. So that's a little bit weird because when you look at aromatic, you think of like stability, and then like some people would think like even number is like a nicer number than odd number, but and then they remember as even as aromatic, and then odd anti-aromatic, but that's not the case, right? Odd pair of electrons is aromatic, even pair is anti-aromatic if you use this way, right? If not, you could use the 4n plus 2 or 4n way as well, right? So this right here is going to be missing one or more conditions. Right, A, B, or C. Okay, so let's look at an example here. Let's look at this benzene ring here. This benzene ring, I think you guys already know like what this benzene ring is, right? Because yes, I think you guys seen it since 2018A as well. But this is the chapter where you look at it more closely, the benzene ring. So this benzene ring right here is cyclic, right? All of the electrons here are in a ring. It's planar because all of the atoms here are sp2 hybridized, sp2, 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 and it's also fully conjugated. There's no sp3 roadblock in the ring, right? So it does fulfill all of these three conditions. So now we have to determine whether it's aromatic or anti-aromatic. So we see three pairs of electrons in the conjugated system. Three pair is an odd pair, which makes it aromatic. Aromatic. Great. So that's what you do to determine this. Now let's do a lot of practice problems, and I'll give you guys some weird ones to keep in mind after we do the practice here, right? There's gonna be two weird examples that you guys need to be careful about. Right? Okay, let's do this one. And then for the electrophilic aromatic substitution, yeah, let's see. I'll introduce you guys the basic general mechanism of it, because electrophilic aromatic substitution, or EAS, there's a lot of reactions that go with that. But if you know the general mechanism behind it, it just follows that same principle for all of the reactions in chapter 15 and chapter 16, right? The only difference is like setting up the electrophile part, but it follows the same mechanism, EAS. And then the next office hours next week, we could go over specifically each of the EAS reactions: nitration, sulfonation, fructose alkylation, fructose acylation, combination chlorination, like all those EAS reactions. Right. So let's say we have this compound here, right? But she won't give you pairs of electrons. You have to figure that out by yourself, like how many pairs of electrons are not drawn here, right? So try this. Use this table to figure out if this molecule is going to be aromatic, anti-aromatic, or non-aromatic. So to guide you guys, let me ask you guys questions. The first thing I look at is the three conditions, right? These three conditions here. Is this is like uh in a ring, resonating in a ring, right? And be careful here. There is a missing pair of electrons, right? Which is the pair of electrons on nitrogen, because since this nitrogen is neutral, it will have 3 bonds and a pair of electrons, right? Or to fill the octet row, it needs a pair of electrons: 2, 4, 6, 8, right? And for conjugation are double bonds, pairs of electrons, carbocations, or radicals, right? So thinking about that, is there resonance or conjugation happening in a ring? Are they planar, and are they fully conjugated? Like these three conditions here. Does this molecule fulfill these three conditions? And if not, which conditions does it not fulfill? Okay, so um, it is going to be considered cyclic because this is a whole ring or cycle right here, and specifically this is a heterocycle, right? Because this ring here, carbon atom, nitrogen, right, which is a heterocycle, right? It is plain because every single atom P2 hybridized, right? Nitrogen here looks, but it's not sp3. It's this pair of electrons here can do resonance, right? that these are the resonance angles that are going to happen between that whole ring right there. Not sp3 resonance. Wait, it looks sp3. Sp3 is sp2 because of resonance. Looks sp3, but not. Right? It's not sp3. It is sp2 because it can do resonance. Right? So that is fully conjugated then, because we have sp2, 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 sp3, 2, not sp3, a network of adjacent sp2 like atoms or p orbitals happening. That is full conjugation right there. Fully planar, making it planar. So it does fulfill the now aromatic or anti-aromatic. We there are 3 electrons in this conjugated, I mean 3 pairs of electrons, which is and that makes it aromatic. Right. Okay, let's try another one. Let's try this one here. Okay, determine whether this molecule aromatic and unaromatic using this table here for 1 to 2 minutes. Okay, so this molecule here is, okay, did you guys answer for this one yet? Or if not, we could walk through this problem too. If this molecule is aromatic, anti-aromatic or non-aromatic. Okay, so this structure here is fully cyclic, right? Because all the electrons here are a ring. Like there's 3 fused rings fused together, making the overall structure cyclic. It is also planar because all of the atoms here in the structure are sp2 hybridized, right? Every single atom is sp2, 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 sp2. And because it's planar, and it's like sp2 everywhere with no sp3 roadblock, it's also fully conjugated, right? All of the electrons here can do resonance with each other, making it fully conjugated, right? So now we have to determine how many pairs of electrons are moving. That's going to be 2, 4, 6, 8, 10, 12. So 12 electrons individually, but that's 1, 2, 3, 4, 5, 6 pairs. 6 pairs of electrons, that's even, making this anti-aromatic. Anti-aromatic. Okay. Let's do 4 more of the normal ones. And then I'll give you guys 3 examples of the 3 different weird ones that you guys might encounter. Okay. So let's do these 4 here. Oh, this one right here. Oh, did you guys have an answer for these, whether these are aromatic? Yeah. So the first one here would be non-aromatic because the conditions, it is cyclic, right? Like this, the structure is cyclic. It's a ring. It's not fully conjugated. It is not fully planar, right? And that's because of this sp3 roadblock, right? So since there's no full conjugation in this structure, it's not fully conjugated, right? It can only do resonance um, between these four atoms. So if I draw out the resonance hybrid of that structure, the electrons are only going to be in between those four atoms right there, right? It's not going to go up here, right? So it's not fully conjugated. If it were to be fully conjugated, then electrons would have to go flowing throughout all of the ring, right? Like all of these structures here, the electrons are flowing throughout all of the ring, flowing throughout all of the ring, flowing throughout all of the ring. But this, it only flows partially throughout the ring. So that's not fully conjugated, doesn't fulfill all three conditions, making it non-aromatic. Okay, nice. Did you guys get the second one? For the second one right here, the difference between the second one and the first one is this pair of electrons, right? And then if there's a pair of electrons there, do you know how many I said it, there's gonna be one pair of electrons, right? There's a negative charge, a negative charge on that carbon, giving that carbon a pair of electrons, right? So Levens, she won't give you that pair of electrons. You have to like find that out by looking at the formal charge, right? Because carbon had a formal charge of -1, this carbon will have one pair of electrons right there, right? This pair of electrons right here can do resonance with the structure like that, right? And because it can do resonance, this is very similar to the night. It looks sp3 because it has like 4 groups attached to it. The 3 single bonds, 1, 2, 3, and a pair of electrons, right? But because of resonance, it is sp2, right? Because so it is fully cyclic, it is fully conjugated because we could do resonance throughout the ring. So it's either going to be aromatic or non-aromatic. We have 3 pairs of electrons that are doing resonance, which is an odd pair, making it aromatic. So this structure here is aromatic, right? This pair of electrons here counts as a pair that's doing resonance with the ring, right? Okay. What about the third one?
Non-aromatic, I think, right?
Yes, yes, it is non-aromatic. And why? Why do you say that? You're correct.
Because can't cycle. There's only one bond that can cycle and the other 2 bonds can't cycle. So because it can't cycle, it's non-aromatic.
So it is or cyclic, right? This structure is cyclic right here.
Yeah, it's cyclic, but it can't resonance, you know?
Yeah, it can do resonance. It's not fully conjugated. Right,
Yeah.
right. Yeah, so this is non-aromatic because it's conjugated, right? It is cyclic, but because it's not fully conjugated due to these sp3 roadblocks, it's non-aromatic. Yeah.
All right.
Uh-huh. You got it. You got it. There is a pair of electrons up here, but that pair of electrons is stuck. Can't do resonance. So this carbon here would be sp3 as well, right? Since that pair of electrons can't do resonance, it is an atom. Right. Okay. What about the fourth one? What did you guys say about the fourth one?
I'm going to say it's not aromatic as well, but it might be aromatic. I don't know. I'm not sure.
Yeah, it's okay. It's okay. Do you have a reason why you're saying it's non-aromatic, or
I don't know if you like, I don't know if it can cycle with like 4 cycling points, like 4 resonance points. I don't know if it can do that.
right? So if you see a carbon with a positive charge here, right? Right. So this one right here, how many pairs of okay? Let's first start with this question. How many pairs of electrons are on this carbon here? How many pairs of electrons?
I
Or
think it's, I
zero,
don't
one,
know.
two, three?
I think it's 3 or 1. I don't know. Or
Yeah.
either 3 or 1.
Right. So since this carbon here has a positive charge, do you
It's
think
gonna be 1, right?
it's gonna be zero? There's
Oh,
no pairs
0.
of electrons. Yeah, no pairs of electrons
All
here.
right, all right.
Right, because you haven't taken general chemistry, right? Like the atoms and stuff like that, like the
Yeah,
periodic
I have
table.
taken. Às vezes that kind of confuse the positive sizes. This
Yeah.
confused me a bit.
No, it's okay. It's okay. So it has no pairs of electrons here because you'll learn that carbon is on the fourth main group on the periodic
Yeah,
table.
yeah, yeah. I
Have you
know
learned about
that.
that? Carbon is on
Yeah,
the fourth
yeah, I
main
know
group on the
that.
periodic table. So if it's on the
And
fourth main group,
hydrogen is like the first element, like it's on the
yes,
first group.
yeah, hydrogen is
So
in the
it
first.
can also it can only connect to like one piece of carbon and nothing else.
Well,
Or
hydrogen
a piece
can
of,
connect to one thing. Like it could be
yeah,
carbon with
only one thing,
yeah,
basically.
it could be
It
like
can connect to two things.
right. Carbon wants to connect to four things because it's on the fourth group.
Yeah.
Right. But this carbon here is only connected to three things. So it's missing a bond. If it's missing a bond, missing electrons, it has a positive charge. Right. So it has zero pairs of electrons there. Zero.
Yeah.
It goes more into detail than that. But then uh, I'll yeah, you'll learn more about that in Gen Chem when you learn more in chemistry.
Hmm.
Like the formal charges and the oxidation numbers. Right. So that carbon there has zero pairs of electrons. Uh, that means that this is fully conjugated because we have a network of orbitals, right? Where all of these electrons can move around, but there's three pairs of electrons, which is an odd pair. And if you look at the table, an odd pair of electrons is aromatic, right? Aromatic. So this structure here would be aromatic.
All right.
Right? So when you think of odd, you think of a bad number, right? So, and then you think of anti, right? But it's actually the opposite. An odd pair represents aromatic structure.
Yeah, I thought it was even
Uh,
because the positive side right there. This got kind of confused, lol.
yeah, there's positive charge. You have a negative charge, then it has a pair of electrons.
Yeah, I know that. This
Depending on
confused
what
me a little
atom
bit.
you have.
Yeah.
Yeah.
Positive side
All right.
confused me a
Let's see.
bit still.
Oh, like the charges here.
Yeah, I know what a negative side is, but positive kind of confuses me sometimes.
Hmm. When you think of positive charge, think of missing electrons, losing electrons. Because do you know what charge electrons have? Like what kind of charge electrons
Negative,
have?
negative.
Yeah, negative, right. So this carbon here, it's missing electrons. It's missing negative charge, right?
Yeah.
Which is why it has a positive charge. That's one way we
Yeah,
can think
yeah.
about it. Yeah.
All right.
Yeah.
I think that every time I see a positive side, just to remember that.
Yeah. When you see positive sign, think of missing electrons.
Yeah, right.
Missing negative charge.
All right.
Okay. So now let's look at the three weird scenarios.
Não, pode. Não, pode, não justifica. Não justifica, mas não, nem explica, nem justifica. Não tem argumento.
That's one weird scenario. Another weird scenario is this one. And then
A coordenadora então falou, ela disse assim, olha, a mãe da menina falou que...
Eu vou arrumar aqui pra dormir, tá? Já vai saindo aí.
is this right here. Boom. Okay.
All right, I'm back. My parents just walked in.
Yeah, that's okay. So let me just go over these weird scenarios with you guys. This structure here is cyclic, right? Because all of the atoms here are in a ring. It is planar because all the atoms here are sp2, 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 sp2. And it's fully conjugated, right? It could do resonance. The tricky part here is determining how many pairs of electrons are participating in the resonance structure, right? It's only going to be these three pairs right here. 1, 2, 3. Right?
Yeah.
This pair of electrons here is not in the conjugated system. It's not part of the resonance system, not in the conjugated system. Right. And then the way that you can think about that is because it's on a double bonded atom, right? This pair of electrons is on the nitrogen that is double bonded. You see that double bond right there?
Yeah.
Is that double bond?
And nitrogen in the fourth group as well, all right?
It should be in the fifth group. Nitrogen should be in the fifth group.
All right.
Fifth
I
group
can't
of the
forget
periodic
which
table.
group is nitrogen is in. I can't forget sometimes.
Yeah, it's okay. In OChem, there's only a few elements that you see a lot, like carbon, especially because like OChem is like all carbon and hydrogens.
Yeah.
Nitrogens, oxygens, the halogens. Sometimes like phosphorus, the metal, magnesium. But
All right.
there's only a few elements in the periodic table.
So it will be so to have like two electrons because it's a nitrogen atom connected to three carbon atoms. Well, one singular bond and one double bond. So yeah.
Yeah, this nitrogen here has one single bond, one double bond, and one pair of electrons.
Yeah,
that
so
gives it
it
5
has
electrons.
two electrons.
1, 2, 3, 4, 5. 2 individual electrons, yes.
Yeah.
Yes, 2 electrons to itself. But it's sharing like 3 bonds. So this nitrogen has 5 bonds, 5 electrons to itself. That's good, right?
Yeah, so it's full. So it's satisfied right now.
Yeah, it's satisfied, right? Neutral charge. No positive charge, no negative charge.
Yeah.
Right. And this double bond right here is gonna be that overlap between the two p orbitals, right? So the p orbitals are taken already, right? This lone pair of electrons right here is not on a p orbital. It is on an sp2 orbital, right? So it's not doing resonance because resonance is gonna happen between p orbitals, between p orbitals.
Yeah, right. Yeah.
Right. So then this right here is just gonna be aromatic because 3 pairs is an odd pair, making it aromatic.
Yeah.
Let's go back to the previous example with NH2. Let me show you the difference between that and this one here. That's good. So the one with NH2 or NH, this one right here, this pair of electrons, right, is part of the resonance structure. Part of conjugated system. Because if you look at the atom that it's on, this nitrogen right here, nitrogen is not double bonded. There's no double bond here, there's no double bond there, right?
Yeah.
So the p orbital here is going to overlap with the other p orbitals, where what holds this pair of electrons is that p orbital, right? That p orbital there is holding that negative charge now. That pair of electrons. That pair of electrons is in a p orbital. P orbital. Okay. The sp2 orbitals are going to be here. Right. That's sp2, sp2, sp2. Okay. Yeah. Great. Whereas the difference here in this structure is that this nitrogen is double bonded, where the p orbitals are holding that double bond between the two atoms, making this pair of electrons in an sp2 orbital, making that pair of electrons stuck right there. Can't do resonance. So it's not part of the resonance structure. Don't count that as a pair of electrons when you're determining if it's aromatic or anti-aromatic. Right.
Hey Brian, I have a question.
Yes.
Can butanes be aromatic?
Butane.
Butanes, like cyclobutanes.
Cyclobutane.
Yeah.
This?
Yeah, the square one, yes.
Yes, so it is cyclic, right? So that fulfills
Yeah.
that condition.
Yeah.
It's not fully conjugated. Right? There's no pairs of electrons. All these atoms here are sp3.
Yeah, but what if you add two double bonds? What would be called though? I don't know that name.
If you have two double bonds like this, right?
Yeah,
Then
yeah,
it would be fully conjugated now.
yeah.
Fully conjugated. But how many pairs of electrons do you see? How many pairs of electrons?
Let me count real quick. One pair electron foi carbon. One pair
Sorry,
foi carbon.
how many pairs? Sorry.
One pair, just one
One.
electron foi carbon.
Right. So this is one pair. This is another pair of electrons. Yeah. Right. So that's gonna be two pairs.
Oh, I thought you were talking about the outlet. I thought about that, lol.
The carbons,
Yeah, agora que eu falei a little bit, I thought you meant the four carbons out at the outer edges.
the carbons, there's four carbons. Four carbons. 1, 2, 3, 4.
Yeah.
4 carbons, right? And there's two pairs of electrons doing resonance, and that's an even pair, making it antiaromatic. So this cyclobutadiene is antiaromatic.
All right,
Right?
got
This
it.
is not cyclobutane anymore. This is cyclobutadiene. Two alkenes.
So it's cyclobutadiene.
Yes, cyclobutadiene.
All right, I refer that to cyclobutadiene now.
Butadiene. Yeah. You see a lot of these structures when you do your research?
What?
Do you see a lot of these structures when you search things up? Like,
yeah, I see a lot of cyclobutadienes.
Yeah. Okay. So for this next one here, when you see a carbonyl, which is a carbon double bond oxygen, right?
Yeah.
This carbon right here is sp2 hybridized, right? So the first thing you do before you like the three conditions, draw out the resonance structure of the carbonyl. Just pop that double bond onto the oxygen right there to get this resonance structure. Right, we're just moving that double bond onto that oxygen to get this resonance structure here.
Yeah.
Right. And then the system that we're looking at is that right there. Ignore the bond to the oxygen. Right. This carbon will have a positive charge because it lost electrons. Right. So
yeah.
This structure here is cyclic. It is fully conjugated because we have sp2, 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 sp2. And it is also planar, right? But how many pairs of electrons do you see here?
Two.
Right. Two pairs of electrons are doing resonance. That's an even pair, making this
Antiaromatic.
Yeah. Right. Even pair, antiaromatic. You got it.
Hmm.
Nice. Antiaromatic. Okay, so the third weird scenario is going to be this right here.
Yeah.
This is cyclic. This is fully conjugated, right? But look at the planar thing here, right? There is a hydrogen here, but to avoid steric hindrance, right? One of the hydrogens is going to be like, let's say, dash. The other hydrogen is going to be wedge, right? Because they're so close to each other.
Yeah.
So they're gonna pucker. They're gonna not be planar anymore. So this is non-planar. And if it's non-planar, what is it gonna be? If it doesn't fulfill one of the three conditions, is it gonna be
Non-aromatic.
non-aromatic? Yes. Non-aromatic. Right. So, and there's like some other things that are also non-planar, like this stop sign, cycloocta tetraene. Right. You're gonna see that this membered ring is gonna be a boat shape, like that. Right. So that's not planar anymore.
Yeah.
So this is also non-aromatic.
Yeah.
Yeah. So this is non-planar because of the steric hindrance going on here.
Yeah, like it ain't a flat plane. It's just they one had to have to going up and one going down.
Yes. One going up, one going down. And one's going up. You would expect these hydrogens to be flat and planar, right? Because it's on an sp2 carbon, but it's not going to be flat and planar. Yeah, it's still sp2, but because of the geometry of it, it breaks that rule, right? Usually when you see sp2 atoms, everything is flat and planar, but this is an exception right here. These carbons here are sp2 still, but it's not flat and planar anymore. The hydrogens, one's gonna go up, one's gonna go down to make this side go up and this side go down. In most cases, all sp2 carbons or atoms are flat and planar. In cases like this, where the geometry is weird, then that's when this sp2 carbon is not flat and planar. Yes. There's a very few rare examples that some sp2 atoms they're forced to pucker, right? Because these carbons here are still sp2, but because of the surrounding environment, it forces it to be not flat and planar. Right? Like these sp2 here are not flat and planar. One of the hydrogens is going up, one of the hydrogens is going down. Yeah, with steric hindrance, let's do that. sp2. Let's see. Yeah, so this one right here, right? What I'm saying right now is that that's the only one. Like this right here is the only one that has sp2 atoms that is non-planar, right? Like all the other ones I'm seeing here, like they don't have anything like that. And this is the only structure that I know that's sp2 and non-planar. Like I haven't seen any other sp2 atom that is non-planar as well. Like this is the only structure. This is very distinguishable. Like these two six-membered, well, they're not six-membered rings. They're one ring, right? They're, let's say, one, two, three, four, five, six, seven, eight, nine, 10. 10 carbon membered rings, right? These structures here called an aniline, or specifically a 10 aniline, are the only structures I know that have sp2 atoms that are non-planar, right? I don't know any other structures that are sp2 and non-planar. These are the only structures I know that are sp2 and non-planar. Right. So I haven't seen another example that is sp2 and non-planar. These are the ones I know. Yeah, these are the weird guys. Yeah. Okay. Great. Let's see. This ones here, the boats are also non-planar, right? Like even though all atoms here are sp2 hybridized, the overall structure is non-planar, right? But if you look at the individual carbons, you could say that in that plane they're planar, right? But the overall structure is non-planar because it's like a boat shape. If it's planar, then it has to be flat, this. But the boat one is going like they're wedged up. They're going up like that. Okay. So yeah, the weirdest example is probably the non-planar rings. So this is weird example A, weird example B, weird example C. A is when the pair of electrons is on a double bonded atom. B is when you have a carbonyl, right? And then C is the weirdest one, the non-planar rings. She'll let you know what probably like Nisiri, she made the test so that you don't have to worry about this non-planar thing, right? Like you assume that everything's gonna be planar, but for helix, he wants you to know that this and this is non-planar, non-aromatic, right? Those two structures there. For Levens, I don't know how like she will test yet, but I don't know. Yeah, I'll see her notes. Yeah. Any questions on this? Right. So know this structure and this structure, they're non-planar. Dang. That's crazy. Yeah. Uh-huh. No problem. No problem. No problem.
Did you like the first organic chemistry class? I actually understood a lot of stuff, to be honest.
Yeah, there's a lot of stuff going on, huh? A lot of topics going on.
Yeah, and I understood mostly of them. They were the class I understood the most out of them.
Uh-huh.
Like it
Yeah.
was easy to understand after I learned the basics of the chemistry, you know.
Yeah.
Hmm.
You were able to follow along with this outcome class, like it made sense to you.
Yeah, it makes sense to me, this
That-
one.
That's good. That's good. Like
Well,
you
only the aromatic part.
that
The energy state, kinda, to be honest.
yeah, right. You learn about this on YouTube, or what did you learn about this?
Well, about what?
The aromatic stuff. Did you learn about it before?
No, I was
Oh,
learning it with you.
oh, that's interesting.
Yeah, you teach me aromatic stuff.
I teach you the aromatic stuff, and then when you see it in class, when you take chemistry, you'll be like, "Oh, I know this already. I learned it about this."
Yeah, for you.
In office hours. That's good.
Yeah.
Uh-huh. Dang, you have family over at 2 a.m.
They are still awake for some reason because we had visits and they stay awake for a long time because they
Mm.
went somewhere else while I was with my real life friend.
Oh, I see. Do you have school tomorrow?
Nope, I don't. It's
Okay.
Saturday tomorrow.
Oh, Saturday tomorrow for you.
Oh,
Oh.
no. It's no. I commit stupid. Nope. It's Friday for me next day. I'm
Yeah.
stupid. It's
No, no,
Friday.
no, 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 no. It's okay. It's okay. Yeah.
Yeah.
That's good. That's good. And now when you do your research on online to search up chemical structures, when you see that four-membered ring with the two double bonds, you can think of cyclobutadiene.
Yeah.
No.
Yeah, I know now. And you go for F like cyclopropedine and cyclohexadiene and that stuff.
Wait, so diene D with the DI, that's two alkenes, right? If you see
Yeah.
three, that's triene. If you see four, that's tetraene.
Alright, so for hexane will be like a cyclohexadiene. Hold on, are you typing that? This is hard to
Oh, right. So if
spell.
you see a six-membered ring, with three double bonds, then that's called a benzene ring. There's a special name for that ring. It's called a benzene ring. Let me type in the chat.
Oh yeah. I forgot. It's benzene. Yeah, it's benzene. I already
Benzene.
know. Yeah.
Benzene.
I
Right.
kind of forgot about it.
It's okay. It's
No.
okay.
Yeah.
Yeah. There's a lot of stuff going on. A lot of things
Yeah.
to
A lot of
keep track
stuff
of.
that I just forget the stuff that I already know. Lol.
Right, but that's so like crazy. You're 14 and you haven't taken general chemistry yet, and you're already learning organic chemistry stuff.
Yeah. For
You're getting
you.
it so ahead. That's good though.
Yeah. I still need to learn more standard semester though. I know the Bohr model to be honest. That's something I know already.
Right, right. Dang. And your middle school doesn't teach chemistry at all?
Yeah, they don't teach that semester at all at the middle school. And I'm already learning the basically the organic semester view, lol.
Oh my god.
Yeah.
Yeah. So you
You
gotta learn
really,
online.
yeah, you really the best for teaching me the most nerdy stuff ever. For you.
Yeah,
Really
dang,
the
dang.
best.
I'm happy. I'm happy to hear that.
Thanks.
Uh-huh. No problem, Lavi. Okay. Yeah, so I'll let you go to sleep early. So
Alright,
wake up. But
alright.
it's 2 a.m. for you, so it's not early, but
Yeah, it is 2 here for
yeah,
me. I'm
but
already going to sleep.
right. I have to answer a
Hold
lot
on,
of questions correctly.
your
That's
voice is
good.
glitchy a bit.
Yeah. Thank you. When you answered the questions, I was like, "What? Davy knows all this? That's so crazy."
Yeah, for you. I understood what
Yeah.
you said when you explained this stuff. I
Mhm.
understood it.
That's good. That's
Lol.
good. Yeah. I'll see you, Davy.
Alright, see you too. Bye.
Bye. Good night.
See you next week.
Yep. See you next week. Good night.
Good night.